It is lovely to have you here. Tonight we're exploring a question that seems simple at first, but becomes stranger the longer we sit with it. Does the past still exist? When a moment ends, is it truly gone, surviving only in memory and in the traces it leaves behind? Or does modern physics suggest that every event remains somewhere within the structure of space-time, even though we can no longer return to it? As always, before we begin, let me know where in the world you are listening from, and what time it is where you are. It is always fascinating to see how many different places and different moments can quietly meet here at once. And if you enjoy calm, long-form explorations of science, you can support the channel by liking the video and subscribing. It helps more people find these videos while requiring slightly less effort than resolving the nature of time itself. Now, settle in, get comfortable, and let us begin. The past feels gone because human experience divides time into three very different regions. There is the past, which seems finished. There is the future, which appears open and uncertain. And between them is the present, the narrow moment that feels vividly real. This division seems so natural that it is difficult to imagine reality working any other way. The present appears to be where everything happens. The past survives only as memory, evidence, consequence, and record. The future exists as expectation, possibility, and prediction. We remember yesterday, experience today, and anticipate tomorrow. Yet even this simple description contains a mystery. The present never seems to remain present for long. A moment arrives, briefly becomes now, and then slips into the past. The sound of a sentence fades almost as soon as it is spoken. A movement begins, unfolds, and becomes something that has already happened. The present feels real, but it is remarkably difficult to hold still. This creates the familiar image of time as a river flowing steadily forward. Events appear on the horizon of the future, pass through the present, and disappear behind us into the past. We often speak as though time itself is moving. We say that it passes, flies, drags, runs out, or occasionally refuses to cooperate during a long meeting. But what exactly has disappeared when a moment ends? St. Augustine of Hippo wrestled with this problem more than 16 centuries ago. In his Confessions, he observed that time seems perfectly understandable until someone asks us to explain what it is. We use time constantly. We arrange our lives around it, measure it with clocks, divide it into units, and complain about not having enough of it. Yet defining its nature is far more difficult than reading the hands of a watch. One important distinction is often overlooked. An event no longer happening is not necessarily the same as an event no longer existing. Consider a conversation that ended yesterday. It is certainly not happening now. The voices are silent, the speakers have moved elsewhere, and the particular exchange cannot simply be resumed from the exact point where it ended. But does that mean the event itself has vanished completely from reality? Or does it remain part of the history of the world, fixed within the sequence of events that led to the present? The same difficulty appears when thinking about a childhood home. Perhaps the building still stands, but the home as it was then has changed. The furniture has moved. The people have aged or left. The arrangement of rooms, objects, sounds, and relationships belongs to an earlier time. That version of the home is no longer present, but its effects may remain in memory, habit, personality, and the physical marks left on the building itself. Light makes the problem even stranger. When we look at the sun, we see it as it was roughly 8 minutes earlier because sunlight requires time to cross the distance to Earth. When astronomers observe the Andromeda Galaxy, they see light that began its journey around 2.5 million years ago. The image entering a telescope is not a picture of what is happening there now. It is evidence of a distant past arriving in the present. That past is gone in one sense. The events being observed are no longer occurring at their original locations, yet their electromagnetic signals still exist and continue travelling through space. A burst of light emitted millions of years ago may cross an observatory tonight and leave a measurable trace inside a detector. The physical world is filled with such traces. Memories are maintained through changing patterns of activity and connection within the brain. Ancient climates leave chemical signatures in ice cores and sediment. Living organisms carry genetic information inherited through long chains of reproduction. Fossils preserve altered remains and impressions of organisms that died millions of years ago. Craters record impacts. Tree rings record seasons. Light records distant stars. Even the present arrangement of matter contains information about earlier events. A glass resting on a table occupies that position because of a long sequence of causes. Someone manufactured it, transported it, filled it, moved it, and placed it there. The past is not visible in its entirety, but the present could not possess its current form without it. This does not prove that past events still exist. A trace is not the same thing as the event that produced it. A photograph of a storm is not the storm. A memory of a voice is not the voice still speaking. Evidence shows that something happened, but it does not automatically tell us what kind of existence that event may still have. Human experience presents a moving now. We feel ourselves advancing from one moment to another, carrying memories of what has happened but no memories of what is still to come. Physics approaches the issue differently. It seeks descriptions of reality that remain valid for different observers, moving in different ways and viewing events from different locations. That creates the first tension. Experience suggests that reality is constantly updating, with each new present replacing the one before it. Physics asks whether the distinction between past, present, and future is truly built into the universe, or whether some part of that division belongs to the way conscious observers encounter time. The past feels gone. That much is immediate and undeniable, but whether it has ceased to exist is a deeper question, and the feeling of loss may not be enough to settle it. For much of human history, time was imagined as something shared by everyone and everything. The sun crossed the sky, seasons passed, shadows moved, and events appeared to unfold within one common sequence. Different people might use different calendars or disagree about the hour, but those differences seemed practical rather than fundamental. Beneath imperfect measurements, there was assumed to be one true time. Ancient philosophers approached time in several ways. Aristotle connected time with change and motion, describing it as a measure of change in relation to before and after. Other traditions treated time as a cosmic order, a cycle, or a background through which events passed. These ideas differed in important ways, but everyday reasoning still encouraged the belief that the universe possessed a single present. The scientific picture became much clearer through the work of Galileo Galilei. Galileo studied falling objects, pendulums, projectiles, and moving bodies, helping establish that motion could be described mathematically. Time became a quantity that could be measured and inserted into physical laws. If the position and velocity of an object were known, its later motion could be predicted using the same temporal scale applied everywhere else. Isaac Newton formalized this picture in the 17th century. In his great work on motion and gravitation, Newton distinguished between ordinary measured time and what he called absolute true and mathematical time. Absolute time, in his view, flowed uniformly by its own nature. It did not depend on clocks, planets, people, motion, or physical change. A clock did not create time. It merely attempted to measure it. This distinction mattered, because real clocks are imperfect. Pendulums can be affected by temperature. Mechanical parts wear down, Sand may flow unevenly through an hourglass. The rotation of Earth itself is not perfectly uniform. Newton's absolute time was therefore not identified with any single device. It was the ideal temporal background against which every clock could be judged. Within classical mechanics, the entire universe could be imagined as sharing this background. At any chosen instant, every object had one definite position and one definite velocity. The moon, a falling apple, a ship crossing an ocean, and a stone rolling down a hill all belong to the same universal moment. This allowed simultaneity to appear simple. Two events were simultaneous if they occurred at the same absolute time. Observers might receive information about them at different moments because sound and light require time to travel. But those delays were treated as measurement problems. Once travel times were corrected, everyone could in principle agree about what happened at the same time. The universe therefore resembled an enormous stage. Space provided the setting. Time supplied the steady rhythm. Matter moved through, both according to physical laws. The scenery could change dramatically, but the stage itself remained unaffected. Clocks were treated like rulers for duration. A ruler measures distance without changing space, and a clock was assumed to measure time without being fundamentally altered by its own motion or location. A clock carried onto a mountain, placed on a ship, or moved through a laboratory was expected to measure the same underlying temporal flow, provided it continued functioning correctly. This picture fits naturally with Presentism. Presentism is the view that only the present moment truly exists. The past existed but has ceased to be. The future may eventually exist, but it does not exist yet. Reality is confined to a universal now that advances steadily, replacing each moment with the next. Under this interpretation, the disappearance of the past seems straightforward. One complete state of the universe exists, then another replaces it. Yesterday's state is no longer real because the universal clock has moved forward. Tomorrow's state has not arrived. Reality occupies one moving slice of time. Classical mechanics appeared to support this view because it was extraordinarily successful. Galileo's principles describe projectile and falling bodies. Newton's laws explain the motions of planets, moons, tides, pendulums, machines, and countless objects encountered in the ordinary life. The same mathematics could predict the return of a comet or the path of a cannonball. Newton's law of universal gravitation showed that the force drawing an apple towards Earth followed the same basic rule that held the moon in orbit. This unification was one of the great achievements of science. It suggested that the universe was governed by orderly laws operating within one shared space and one shared time. The success was so complete that absolute time became almost invisible as an assumption. It seemed less like one possible model and more like common sense written into mathematics. Yet a limitation was hidden inside that success. The movements encountered in ordinary life are extremely slow compared with the speed of light. A passenger train, a racing aircraft, and even Earth moving around the Sun travel at only tiny fractions of that speed. Gravitational differences across familiar distances are also usually small. Under these conditions, the corrections later revealed by relativity are so slight that they can safely be ignored in most everyday calculations. A person walking across a room experiences a relativistic change in elapsed time, but the difference is far too small for an ordinary clock to reveal. Two clocks placed at slightly different heights also tick at marginally different rates because of gravity, though detecting this requires extremely precise instruments. Classical time therefore worked not because it described reality with perfect accuracy, but because it was an excellent approximation within the limited range of human experience. The universe kindly concealed its stranger behaviour until scientists began studying light, electricity, magnetism, and motion at far greater precision. As long as one universal present is assumed, the past can be imagined as a state that has simply been replaced. Everyone shares the same now, and everything earlier belongs to the same vanished past. But if observers cannot agree on one universal present, then the boundary separating what exists from what no longer exists becomes much harder to draw. By the 19th century, physics had developed two remarkably successful ways of describing nature. Newtonian mechanics explained how objects moved, from falling stones to orbiting planets. Electromagnetic theory explained electricity, magnetism, and light. Each framework worked beautifully within its own territory. The trouble began when scientists tried to make them agree. According to Newtonian mechanics, speed should combine in a simple way. If a person walks forwards inside a moving train, an observer beside the track adds the person's walking speed to the speed of the train. If the person walks backwards, the speeds subtract. This rule feels so obvious that it hardly seems like a rule at all. Light refused to cooperate. During the 19th century, the Scottish physicist James Clerk Maxwell brought electricity and magnetism together in a unified electromagnetic theory. Maxwell's equations showed that changing electric fields generate magnetic fields, while changing magnetic fields generate electric fields. These linked fields can travel through space as electromagnetic waves. When Maxwell calculated the speed of those waves, the result matched the measured speed of light. This revealed that visible light is one form of electromagnetic radiation, belonging to the same broad family as radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. The equations predicted one particular speed for electromagnetic waves in a vacuum. Light travels at approximately 300,000 kilometers per second. At that speed, it could circle Earth more than 7 times in a single second. This created an uncomfortable question. A speed measured relative to what? Waves known at the time travelled through physical substances. Sound moved through air. Water waves travelled across water. Vibrations passed through ropes and solid materials. It therefore seemed reasonable to assume that light also required a medium. Scientists called this proposed substance the luminiferous ether. It was imagined as an invisible material filling all of space. Light would move through the ether much as sound moves through air, and the speed predicted by Maxwell's theory would be measured relative to this universal medium. If Earth moved through the ether while orbiting the Sun, then laboratories on Earth should experience an ether wind. Light travelling in the direction of Earth's motion should behave slightly differently from light travelling across it, just as a swimmer's progress depends on whether the water flows with them, against them, or sideways. Albert Abraham Michelson designed an extremely sensitive instrument called an interferometer to search for this effect. The device divided a beam of light into 2 beams travelling along perpendicular paths. Mirrors reflected the beams back, allowing them to recombine and form an interference pattern. A slight difference in travel time should have shifted the pattern. In 1887, Michelson conducted a refined version of the experiment with Edward Morley in Cleveland, Ohio. They rotated the apparatus and repeated measurements while Earth moved through different parts of its orbit. The expected shift did not appear. The result became known as the Michelson-Morley experiment. It did not directly prove that no form of ether could exist, but it failed to detect the motion through the luminiferous ether that standard models predicted. Light behaved as though its measured speed did not depend on the direction of Earth's motion. Physicists attempted to preserve the ether by modifying the behaviour of matter. George Fitzgerald proposed that objects moving through the ether might physically contract along the direction of motion. Hendrik Lorentz developed the mathematics much more fully. introducing transformations that connected measurements made in different moving frames. The Lorentz transformations showed that lengths, times, and simultaneity would have to change in precise ways as relative speed increased. Within the ether picture, these effects were often treated as physical adjustments that concealed motion through the underlying medium. Albert Einstein took a more radical step in 1905. Rather than explaining why the ether remained hidden, he removed the need for it. Einstein's special theory of relativity began with two principles. The first stated that the laws of physics are the same in every inertial frame. An inertial frame is a viewpoint moving at constant velocity without acceleration. No smoothly moving laboratory possesses a special claim to absolute rest. The second principle stated that every inertial observer measures the same speed for light in a vacuum, regardless of the motion of the light source or the observer. This sounds impossible if ordinary speed addition is assumed. Imagine a spacecraft moving towards a beam of light. Classical reasoning suggests that the spacecraft should measure the light approaching faster than an observer who is standing still. Yet special relativity says both observers measure the same value. The universe preserves the speed of light by allowing space and time to adjust. Observers moving relative to one another disagree about lengths. They disagree about the durations between events. Most importantly, they can disagree about whether spatially separated events occur simultaneously. Time dilation means that a moving clock accumulates less elapsed time between shared events than a clock following a different path. Length contraction means that distances measured along the direction of motion become shorter relative to another observer. These effects are not separate tricks. They're connected consequences of the Lorentz transformations. At ordinary speeds, the differences are minuscule. A person walking down a street does experience relativistic time dilation, but the change is far too small to notice. At speeds approaching the speed of light, however, the effects become substantial. Relativity does not merely say that moving clocks look slow because their signals take time to arrive. After observers separate and later compare clocks directly, the clocks can genuinely display different elapsed times. Each clock measures its own proper time, meaning the time accumulated along its particular path through space-time. This has been confirmed repeatedly using atomic clocks, rapidly moving particles, and technologies that require relativistic corrections. Unstable particles called muons survive longer when moving at high speed, exactly as time dilation predicts. Their extended lifetimes allow many more of them to reach Earth's surface after forming high in the atmosphere. Time is therefore not one universal substance flowing identically for everything. The amount of time between events depends on motion and on the path followed. Once this is accepted, the old universal clock begins to break apart. There is no single background time against which every observer's clock can be corrected. Different observers can measure different durations without either clock malfunctioning. The disappearance of the past had seemed simple when everyone shared one present. A moment existed everywhere, then gave way to the next. But once motion changes how observers divide events into past, present, and future, the boundary of now is no longer universal. Light did more than reveal a limit on speed. It forced physics to abandon the idea that the entire universe advances according to one shared clock. The most unsettling consequence of special relativity is not simply that moving clocks tick at different rates. It is that observers moving relative to one another can disagree about which distant events are happening now. This principle is called the Relativity of Simultaneity. It states that two spatially separated events judged simultaneous by one observer may occur at different times according to another observer moving relative to the first. Neither observer is mistaken. Each is using a valid inertial frame, and special relativity gives no reason to treat one frame as the universe's preferred viewpoint. Albert Einstein illustrated this with a thought experiment involving a moving train and a railway embankment. Imagine a long train travelling smoothly along a straight track. At the exact moment the midpoint of the train passes a person standing beside the railway, lightning strikes the front and rear ends of the train. The flashes leave visible marks on the track, allowing the observer beside the railway to determine that the strikes occurred at equal distances from where they were standing. Light from both strikes travels towards the observer. If the two flashes reach the person at the same moment, the observer concludes that the lightning strikes were simultaneous in the railway frame. Now consider a second observer sitting at the midpoint of the moving train. At the instant the lightning strikes occur, this passenger is moving towards the place where the front strike happened and away from the place where the rear strike happened. Because light travels at the same speed relative to every inertial observer, the passenger does not explain the difference by saying that one beam of light moved faster than the other. Instead, the passenger receives the light from the front strike before receiving the light from the rear strike, and concludes that the front strike happened first. The observer beside the railway says the strikes were simultaneous. The observer on the train says they were not. This disagreement is easy to misunderstand. It is not merely caused by the light taking different amounts of time to reach the two observers. Both observers understand that light has a finite speed. Both can correct for signal travel time using clocks and rulers within their own frames. Even after those corrections are made, they still assign different times to the two events. The issue is not poor eyesight, delayed reactions, inaccurate equipment, or a passenger who has perhaps had a particularly confusing journey. The disagreement follows from the geometry of special relativity. To define distant events as simultaneous, an observer must establish a network of synchronized clocks. Einstein described a method using light signals. Two clocks at different locations are synchronized by assuming that light takes the same amount of time to travel in each direction between them. This procedure works consistently within a particular inertial frame. However, clocks synchronized in one frame are not generally synchronized according to an observer moving relative to that frame. Each observer constructs a different set of distant events labelled as occurring at the same time. The difference is usually too small to notice in everyday life. Trains move extremely slowly compared with light, so ordinary disagreements in simultaneity amount to tiny fractions of a second. But the principle remains true at every relative speed. As distances and velocities increase, the difference can become substantial. One way to picture this is to imagine spacetime as a map containing every event. An observer divides that map into layers representing earlier times, the present moment, and later times. An observer moving differently cuts through the same spacetime at a slightly different angle. The two observers agree about the events themselves. They agree that the lightning struck the train. They agree about where the strikes occurred and about any later marks or damage. What differs is the way they organize distant events into simultaneous slices. There are important limits to this disagreement. Observers cannot reverse the order of events when one event can physically cause the other. Suppose one person presses a button and a nearby lamp turns on after receiving an electrical signal. Every observer agrees that the button was pressed before the lamp illuminated. The two events are causally connected because a signal travelling at or below the speed of light can pass from the first to the second. Events linked in this way are separated by a timelike or light-like interval. Their causal order is preserved for all observers. A cause cannot become its own effect merely because someone cycles past at an impressive speed. The order can vary only for events that are space-like separated. These events are so far apart and occur so close together in time that no signal travelling at or below the speed of light could connect them. One observer may say the first event happened earlier. Another may say the second happened earlier. A third may regard them as simultaneous. This does not create a contradiction because neither event could have caused the other. A dramatic illustration is the Andromeda paradox, often associated with the physicist and mathematician Roger Penrose. The Andromeda galaxy lies roughly 2.5 million light-years from Earth. Because of that enormous distance, even a tiny difference in an observer's motion changes which distant Andromeda events are assigned to the observer's present. Imagine two people passing one another on Earth. One walks towards the Andromeda galaxy while the other walks away from it. Their walking speeds are insignificant on a cosmic scale, yet relativity gives them slightly different surfaces of simultaneity. When those surfaces are extended all the way to Andromeda, the difference can correspond to events separated there by days. In an exaggerated fictional example, one observer's present might include an Andromedan civilization deciding to launch a fleet, while the other observer's present lies before that decision. The paradox does not mean either person can look through a telescope and instantly discover what Andromeda is doing according to their chosen frame. The light reaching Earth tonight left the galaxy roughly 2.5 million years ago. Information about the imagined decision would require another 2.5 million years to arrive. Nothing observable changes merely because someone turns around and walks in the opposite direction. No message travels faster than light, and no distant event is caused by the movement of a pedestrian on Earth. The example reveals a difference in how valid observers assign times to remote events, not a magical ability to rearrange Andromedan affairs through a gentle stroll. Still, the implication is profound. Strict Presentism says that only events occurring now truly exist. The past has ceased to exist, while the future does not yet exist. But relativity provides no universal agreement about which distant events belong to now. If one observer says a distant event is present while another valid observer says it lies in the past, which observer identifies the events that truly exist? Special relativity offers no hidden universal frame that can settle the dispute. A presentist can attempt to add a preferred frame of reference, declaring that one particular slicing of spacetime represents the real present, yet standard special relativity does not identify such a frame, and experiments have not revealed one. The difficulty reaches directly into the question of whether the past still exists. An event judged past by one observer can be judged present, or even future, by another observer moving relative to the first, provided the event is space-like separated from them. This does not prove that every past event exists eternally. It does show that the boundary between an existing present and a vanished past cannot be drawn in one observer-independent way across the entire universe. There is a present here, along an observer's immediate experience. But there is no single cosmic now stretching through all of space, agreed upon by everything everywhere. Special relativity did more than alter the way physicists measured time. It suggested that space and time were not separate backgrounds after all, but different aspects of one larger structure. The person who expressed this idea most clearly was Hermann Minkowski, a mathematician who had once taught Albert Einstein. In 1908, Minkowski presented a geometric formulation of special relativity that united 3 dimensions of space with 1 dimension of time. Together, they formed a 4-dimensional framework called Spacetime. This was more than a convenient diagram. It changed the language used to describe physical reality. In ordinary life, we identify an object by saying where it is. A book rests on a table, a person stands beside a window, a planet occupies a particular region of space. Yet location alone is not enough to identify a physical occurrence. The book may be on the table in the morning and on a shelf by evening. A complete description must include both where and when. A specific place at a specific moment is called an event. A lightning strike at one end of a railway platform is an event. So is the arrival of its light at an observer's eyes. A clock displaying midnight in a laboratory is another event. Every collision, emission, measurement, heartbeat, and quiet decision can be assigned a position within space-time. An event does not need to be dramatic. In physics, the word simply refers to something located at a definite point in space and time. Space-time is therefore not filled only with spectacular happenings. It contains the entire arrangement of physical occurrences, including many that would struggle to attract much attention at a dinner party. An object does not occupy just one event. As it continues through time, it passes through a sequence of events. This history is called a world line. Imagine marking the position of a person once every second. Each mark represents an event. Joined together through space-time, the marks form the person's world line. A stationary object follows a world line that remains in roughly the same spatial location while extending through time. A moving object follows a tilted path because its position changes as time passes. Light also traces paths through space-time. Because light travels at a fixed speed in a vacuum, its paths define the boundary between events that can influence one another and events that are too widely separated for a causal signal to connect them. Minkowski's framework made the relativity of simultaneity easier to understand. Different observers do not disagree because they inhabit different universes. They assign different coordinates to the same space-time. One observer may divide space-time into a series of flat surfaces, with every event on one surface labelled as happening at the same time. Another observer, moving relative to the first, uses a different set of surfaces. Their slices through space-time are tilted relative to one another. Each observer therefore identifies a different collection of distant events as present. The events themselves do not move around because an observer changes speed. What changes is the division of those events into past, present, and future. The structure remains the same, while the coordinate system used to describe it changes. This resembles mapping the same landscape with different grids. One map may measure distances from north to south and east to west. Another may use axes rotated at an angle. The coordinates change, but the hills, rivers and roads do not rearrange themselves out of politeness. Relativity requires some physical quantities to remain unchanged despite these differing descriptions. The most important is the space-time interval. Two observers may disagree about the spatial distance between a pair of events. They may also disagree about the amount of time separating them. Yet when those spatial and temporal measurements are combined in the precise way required by special relativity, both observers calculate the same space-time interval. The relationship can be expressed in words as follows. The squared space-time interval equals the speed of light squared multiplied by the squared time separation minus the squared spatial separation. Different observers may assign different values to the time separation and spatial separation, but the final interval remains invariant. This invariant quantity helps determine whether two events can be causally connected and how much time can be measured along a path between them. That measured duration is called proper time. Proper time is the time recorded by a clock that travels directly along a particular world line between two events. It is not a universal amount imposed from outside. It belongs to the path taken through space-time. If two clocks begin together, follow different routes, and later reunite, they may record different amounts of proper time. One might remain on Earth while the other travels at very high speed before returning. Their disagreement is not caused by poor calibration. Each clock has measured the genuine duration of its own world line. Time is therefore woven into the history of each object. It is not one invisible river carrying everything forward at the same rate. This geometric picture inspired an interpretation often called the block universe. In philosophy, the closely related view is known as Eternalism. According to Eternalism, past, present, and future events all belong to the complete structure of space-time. The universe is not imagined as a three-dimensional world that is repeatedly replaced by a new version. Instead, reality is treated as a four-dimensional totality containing events at different locations and times. A person's birth, present life, and later events would all occupy different regions of the same space-time structure. They would not all be experienced at once, just as a traveller does not occupy every point along a road at once. Nevertheless, each location belongs to the road. This interpretation fits naturally with relativity because no universal present divides space-time into one real slice and many unreal ones. If different observers identify different distant events as present, it becomes difficult to argue that only one of those collections exists. Still, the block universe must be described carefully. It is not a separate object that physicists have photographed, detected, or placed inside an experiment. It is an interpretation of the mathematical and physical structure described by relativity. Relativity has been tested with extraordinary precision. The claim that all events equally exist is a philosophical conclusion drawn from that structure, rather than a direct measurement made by an instrument. The existence of an event within space-time also does not mean that it is still happening. A birthday celebrated years ago would occupy an earlier region of a person's world line. In the block universe picture, that event remains part of space-time. Yet the person located later on the world line is not still experiencing it. The candles are not continuing to burn. The guests are not trapped in an eternal afternoon, patiently waiting for the universe to move on. Events are located at particular times in the same way that places are located at particular positions. London existing does not mean someone in Oxford is currently standing in London. A mountain existing does not mean every traveller can reach its summit instantly. Existence and present accessibility are different ideas. The same distinction applies to the past. An event may belong to space-time without remaining reachable from a later event. A world line moves through events in a causally ordered direction. Ordinary observers cannot simply turn around within time, as they might change direction while walking across a room. The past might therefore be real without being available. Yesterday afternoon could remain part of space-time while still being inaccessible to someone living today. Its events would occupy earlier positions along world lines, connected to the present through causes, memories, records, and physical consequences. Nothing in that description implies that a person can return there, observe it again, or change what occurred. The block universe offers one answer to the mystery of where the past went. Perhaps it did not go anywhere. Perhaps events do not vanish from reality when they cease to be present. They remain where they always were, at their own locations in space-time. What changes is not the event, but the position of the observer along a world line and the collection of events that observer can experience, influence, or receive information from. In this view, the past is not still happening. It is simply still there. Every event in space-time is surrounded by a structure that determines what can influence it, what it can influence, and what remains causally disconnected from it. This structure is called a light cone. The name comes from the way the paths of light appear when drawn on a space-time diagram. Imagine a single event, such as a lamp flashing briefly in an otherwise dark room. Light spreads outward from that vent in every spatial direction at approximately 300,000 kilometers per second. On a diagram with space shown horizontally and time extending vertically, the expanding sphere of light forms a cone. A second cone extends into the past, representing all earlier light signals that could arrive at the event. Together, these regions divide space-time into a causal past, a causal future, and a space-like separated elsewhere. The past light cone contains every event capable of sending a signal to the present event at or below the speed of light. A sound heard now belongs to the past light cone because it was produced earlier and travelled through the air. Light entering the eyes belongs there as well. So do radio transmissions, gravitational influences, and any physical cause that has had enough time to reach the observer. The future light cone contains events that the present event could potentially influence. A beam of light switched on now can affect matter elsewhere later. A spoken sentence can alter another person's thoughts after sound crosses the space between them. A spacecraft launched from Earth may eventually reach a distant region, provided that region lies within the future light cone of the launch. Everything outside both cones belongs to the space-like separated elsewhere. These events are too distant and too close in time for any signal travelling at or below the speed of light to connect them with the event at the centre. This division gives space-time its causal structure. It also reveals that looking across space is always looking into the past. Light does not travel instantly. The moon is seen roughly 1¼ seconds in the past because moonlight takes that long to reach Earth. Sunlight takes about 8 minutes and 20 seconds to cross the average distance between the Sun and Earth. If the Sun could somehow change suddenly, Earth would continue receiving its earlier light for those additional minutes. The planets appear as they were minutes or hours ago, depending on their changing distances from Earth. The nearest large galaxy, the Andromeda Galaxy, is seen as it existed roughly 2.5 million years ago. Light from very distant galaxies may have travelled for more than 13 billion years before reaching modern telescopes. Astronomy is therefore an unusual kind of history. Telescopes do not merely observe different places, they observe different times. The James Webb Space Telescope can detect infrared radiation that began travelling when the universe was a small fraction of its present age. The cosmic microwave background carries information from roughly 380,000 years after the Big Bang, when the early universe cooled enough for light to travel freely across space. These observations reveal genuine earlier states of the universe. They do not show how distant objects are at the moment the observation is made on Earth. A star seen tonight may already have changed significantly. It may have expanded, exploded, or disappeared, while its older light continues to cross space. Until a later signal arrives, observers on Earth cannot know its more recent condition through direct observation. This is not merely a limitation of telescope design, it is built into causality. No information can arrive faster than light in a vacuum, according to special relativity. The distinction between causally connected and space-like separated events also explains why relativity can allow disagreements about temporal order without permitting ordinary contradictions. All observers agree on the order of causally connected events. If one event sends a signal that produces another, then every valid observer agrees that the cause occurred before the effect. The numerical time assigned to each event may differ between coordinate systems, but their causal order remains unchanged. Suppose a star emits a photon and a telescope later detects it. Every observer agrees that the emission occurred before the detection. The telescope cannot detect a photon before the photon exists. The two events are connected by a light-like path. The same is true for slower physical influences. A person pushes a cup and the cup moves. A radioactive nucleus decays, and a detector records the emitted particle. A lightning strike heats the surrounding air, and thunder later reaches a listener. Cause precedes effect. This principle is called causality. Causality does not mean that every earlier event causes every later one. It means that physical influence is restricted by the light cone. Causes can affect only events lying within their future light cones, while effects can originate only from events within their past light cones. Space-like separated events are different. Because no signal could travel between them in time, observers may disagree about which happened first. One frame may assign event A an earlier time, another may assign event B an earlier time, a third may call them simultaneous. No causal contradiction appears because neither event could have influenced the other. The past light cone also changes as an observer advances along a world line. At each new event in a person's life, the past light cone reaches farther into surrounding space-time. Signals that were once too distant to arrive may eventually cross into the observer's causal past. Imagine a supernova exploding in a galaxy 1,000 light-years away. For the next 1,000 years, the explosion remains outside Earth's past light cone. It has occurred at its own location, but no signal from it has yet reached Earth. When the light finally arrives, the supernova becomes part of Earth's observable past. Telescopes may record its changing brightness, spectra, and expanding debris. An event that was previously inaccessible now leaves physical evidence in detectors, computers, and human memory. This gradual arrival of information means that the observable past is not fixed in size. It grows continually. Every second, Earth receives light and other signals from regions slightly farther away in space-time. The universe quietly delivers old news, although some of it has been travelling for several billion years and may reasonably be excused for lacking urgency. Events outside the current light cone require careful language. A distant event that is space-like, separated from an observer, is not part of that observer's causal past or causal future. Different frames may classify it as earlier, simultaneous, or later. It may therefore be misleading to call such an event objectively past or objectively future before a causal relationship becomes possible. Relativity preserves clear past and future relations, where signals can connect events, but it does not assign one universal temporal order to every pair of events in the universe. Light cones refine the question of whether the past still exists. Instead of imagining one enormous past shared identically across all of space, physics distinguishes the causal past of each event. This is the region that can still influence the observer through arriving light, matter, gravitational effects, records, and other physical signals. Some portions of space-time remain permanently inaccessible. Others become observable only after long delays. Still others have already influenced the present so deeply that the current world could not exist without them. The past is therefore not simply everything behind one universal moment. It is organized by causal connection. For any observer, the most physically meaningful past is the region of space-time from which influence can still arrive. Special relativity showed that motion changes the amount of time measured between events. Yet, it still dealt mainly with observers moving at constant velocity through regions where gravity could be ignored. Albert Einstein soon began searching for a broader theory, one capable of describing acceleration and gravitation as well. The result was the general theory of relativity, completed in 1915. In Isaac Newton's physics, gravity was a force acting across space between objects with mass. Earth pulled the moon. The sun pulled the planets. A falling stone accelerated because Earth exerted a gravitational force upon it. General relativity replaced this picture with something more geometric. Matter and energy change the shape of space-time, while objects and light follow paths through that curved geometry. Gravity is therefore not simply an invisible pull passing between bodies. It is the behavior of objects moving through distorted space-time. The full theory relates space-time curvature to energy and momentum. Mass contributes to that curvature, but so do pressure, radiation, motion, and other forms of energy. A planet changes the geometry around it. A star produces a stronger distortion. A black hole curves space-time so severely that an event horizon forms, beyond which light cannot escape to distant observers. Curved spacetime also changes time itself. A clock located deeper within a gravitational field accumulates less proper time than a clock positioned farther away. This effect is called gravitational time dilation. Near Earth, the difference is small but real. A clock at sea level ticks slightly more slowly than an otherwise identical clock on a mountain. The higher clock lies farther from Earth's centre and therefore sits in a slightly weaker gravitational field. Over ordinary human timescales, the difference is tiny, but sufficiently precise clocks can measure it. It is sometimes said that gravity slows time. This is useful shorthand, though it should be handled carefully. Each local observer sees their own nearby clock ticking normally. A person at sea level does not feel their thoughts dragging behind those of someone on a hill. The difference appears when clocks following different paths through curved space-time are compared. One of the earliest direct laboratory tests involved gravitational redshift. In 1959, physicist Robert Pound and his graduate student Glenn Rebka performed an experiment in the Jefferson Physical Laboratory at Harvard University. They used gamma rays travelling through a vertical height of roughly 22 meters. General relativity predicted that radiation climbing upward through Earth's gravitational field would lose frequency when measured by a higher observer. This does not mean photons gradually become tired during the climb, despite the tempting image. Instead, the frequency shift reflects the fact that clocks at different gravitational potentials do not measure time at exactly the same rate. Pound and Rebka used the Nussbauer effect, which allows extremely precise measurements of gamma-ray absorption and emission in solid materials. Their experiment detected the predicted gravitational redshift, providing important evidence that gravity affects the passage of time even across the modest height of a laboratory building. The same principles were tested on a larger scale in 1971 by physicists Joseph Haffel and Richard Keating. They placed highly accurate cesium atomic clocks aboard commercial aircraft and flew them around Earth, first eastward and then westward. Other clocks remained at the United States Naval Observatory as references. The airborne clocks were affected by two different relativistic processes. Their motion produced time dilation described by special relativity. Their higher altitude placed them in a weaker gravitational field, causing them to accumulate more time according to general relativity. The precise result depended on the direction of travel, because Earth itself rotates. Eastward and westward flights had different speeds relative to a non-rotating reference frame centered on Earth. When the clocks were reunited, they displayed small but measurable differences. The results were broadly consistent with the combined predictions of special and general relativity. The clocks had not merely appeared to run differently while separated. They had genuinely accumulated different amounts of proper time along different world lines. Relativistic time dilation is now part of everyday technology, even though most people can use that technology without giving curved space-time much thought. The global positioning system depends on satellites orbiting more than 20,000 kilometers above Earth. Each satellite carries precise atomic clocks and transmits timing signals used by receivers to calculate location. Because the satellites are moving rapidly, special relativity makes their clocks run slightly more slowly than clocks on Earth. Because they orbit in weaker gravity, general relativity makes them run more quickly. The gravitational effect is larger. Without correction, the combined difference would cause the satellite clocks to gain roughly 38 millionths of a second per day, relative to clocks on Earth. That may sound negligible, yet light travels almost 300 meters in 1 millionth of a second. An uncorrected timing error would therefore produce navigation errors that grew by several kilometers each day. The global positioning system works accurately because relativity is built into its clock rates, calculations and operating procedures. Modern clocks can detect far smaller gravitational differences, Researchers at the National Institute of Standards and Technology have developed optical atomic clocks that use electromagnetic radiation at visible or near visible frequencies, rather than the microwave frequencies used by traditional cesium clocks. Their extremely rapid oscillations allow extraordinarily precise measurements of time. Experiments using optical clocks have detected differences in ticking rates between clocks separated vertically by only centimetres. Moving a clock slightly higher changes the gravitational potential enough to produce a measurable difference. At this level of precision, placing a clock on a shelf rather than the floor becomes a relativistic decision. Fortunately, most alarm clocks remain too imprecise to use general relativity as an excuse for getting up late. These experiments confirm a deeper principle. There is no cosmic master clock whose reading defines the true age of every object. Elapsed time depends on the world line followed through spacetime. Motion affects proper time. Gravity affects proper time. Two objects may begin together, travel through different regions or at different speeds, and reunite having experienced unequal durations. Neither clock needs to be wrong. Each records the length of its own path through four-dimensional spacetime. This strengthens the geometric view of history. A planet orbiting a star, a photon crossing a galaxy, a clock resting on Earth, and a person travelling aboard an aircraft all trace world lines through the same curved structure. Their histories are not arranged against an independent temporal background. Time is built into the geometry those histories follow. Two observers can therefore separate and meet again with different amounts of aging behind them. One may have experienced more heartbeats, chemical reactions, and seconds than the other. They share the events of departure and reunion, but the durations between those events are not universally identical. The past cannot be divided into one perfectly shared sequence, measured by a single clock for the entire universe. Every object carries its own proper time along its world line. Gravity does not merely influence what happens within time, it helps determine how much time exists between one event and another. There are several ways to answer the question of whether the past still exists, and each begins by deciding what existence means across time. The first view is called Presentism. Presentism says that only the present moment exists. Past events once existed, but they no longer do. Future events may eventually become real, but they do not exist yet. Reality is therefore limited to whatever is happening now. This closely matches ordinary experience. A conversation ends, a season passes, a person grows older. The earlier moment appears to vanish as a new one replaces it. The present seems privileged, because it is the only time in which events are experienced directly, choices are made, and physical changes occur. Presentism preserves a strong sense of becoming. The world is not merely arranged across time, it is continually coming into existence. The future remains open, the present becomes actual, and the past falls away. This makes change feel genuine. A flower does not simply occupy different temporal locations within a larger structure. It truly begins to bloom, becomes fully open, and later withers. According to presentism, reality itself changes as one present replaces another. The difficulty is that presentism requires a clear answer to a deceptively simple question. Which events belong to the present? Within Newtonian physics, the answer appeared straightforward. Absolute time supplied one universal now shared across the entire universe. Every existing object could be imagined as occupying the same temporal slice. Special relativity removes that shared slice. Observers moving relative to one another can disagree about whether distant events are simultaneous. One observer may classify an event as present, while another valid observer places it in the past or future. Standard special relativity does not identify one of those observers as secretly correct. This creates a serious problem for strict presentism. If only the present exists, but physics provides no observer-independent present extending across space, then it becomes unclear which distant events possess reality. Some versions of presentism respond by proposing a hidden preferred frame of reference. In this picture, one particular division of space-time represents the true present, even though ordinary observations do not reveal it. A preferred frame would restore an objective simultaneity. It would allow the universe to possess one real now beneath the different measurements made by moving observers. However, this addition goes beyond the usual symmetric formulation of special relativity. The theory treats all inertial frames as physically equivalent, and no experiment has established a hidden frame that defines absolute rest or universal simultaneity. Cosmology offers something related but not identical. In models of a large-scale homogeneous and expanding universe, cosmic time can be defined using ideal observers moving with the average cosmic expansion. This provides a useful measure of the universe's age. Cosmic time does not restore Newton's absolute time in every situation. It depends on the approximate large-scale structure of our universe and does not overturn the local predictions of relativity. It may offer a natural reference frame for cosmology, but whether it can serve as the metaphysically real present is a further philosophical claim. A second view is eternalism. Eternalism holds that past, present, and future events are all equally parts of reality. They occupy different positions in space-time, just as different locations occupy different positions in space. A person experiences only a limited region along a world line. That does not mean events elsewhere on the world line are unreal. A childhood birthday, the present moment, and a future event may all belong to the complete four-dimensional structure, although they are not experienced simultaneously. This interpretation fits naturally with Minkowski spacetime. Since different observers divide the same spacetime into different collections of simultaneous events, eternalism avoids selecting one collection as uniquely real. The present becomes local and perspectival. It describes where an observer is along a world line rather than identifying the only layer of reality that exists. A geographical comparison can help. A traveller in Edinburgh may call Edinburgh here, while someone in Paris calls Paris here. Neither believes that only their own location exists. The word here identifies a perspective within space. Eternalism treats now in a similar way. Each observer experiences a particular event as now, but this does not require every other temporal location to be unreal. This gives eternalism a close relationship with the block universe. The universe is represented as a four-dimensional totality containing complete physical histories. Objects do not merely occupy space while changing through an external time. Their entire trajectories form extended structures within space-time. Yet eternalism faces a different challenge. Human experience does not feel like the observation of a static block. Time appears to pass. Events seem to become real. The future feels open while the past feels settled. Conscious awareness seems to move from one moment to another, rather than existing as an unchanging line spread across space-time. Eternalism must explain why reality appears dynamic from within, if the full history already belongs to the structure. Some defenders argue that change does not require the block itself to change. Change means that an object has different properties at different times. A tree is bare in winter and covered in leaves during summer. Both states occupy different temporal regions, and the contrast between them is genuine. From this perspective, asking the entire block universe to change would be like asking a complete map to travel. The map contains movement as paths between places, even though the paper does not need to walk anywhere itself. That answers part of the difficulty, but it does not fully explain the felt passage of time. Why consciousness presents one moment as vivid, another as remembered, and another as anticipated remains an open problem involving physics, neuroscience, and philosophy. The third major view is the growing block universe. According to this interpretation, the past and present exist, but the future does not yet exist. Reality resembles a four-dimensional block that continually grows as new events become actual. The growing block preserves the past instead of allowing it to vanish. Yesterday remains part of reality, and the present forms the advancing edge at which new events are added. The future stays genuinely open. This offers an appealing compromise. Like Eternalism, it treats the past as real. Like Presentism, it preserves objective becoming and gives the present a special role. The model also fits the intuitive difference between memory and anticipation. Records point towards an existing past, while the future contains possibilities that have not yet been decided. Its central difficulty is locating the growing boundary. Relativity provides no universal present surface on which the block can expand. Different observers identify different sets of distant events as simultaneous. If reality grows, physics must explain where its objective edge lies, and why that boundary has a physically privileged status. A growing block could introduce a preferred frame, but this encounters the same challenge faced by presentism. The additional structure is not supplied directly by standard relativity. There is also a curious problem concerning awareness. If all past moments continue to exist, then past observers within the growing block presumably felt that they occupied the present. A person living yesterday believed they were located at reality's advancing edge. If only the true boundary is genuinely present, it becomes difficult to explain why observers located within the existing past possess experiences that seem equally immediate from their own perspectives. Each interpretation therefore preserves something important. Presentism protects the uniqueness of now, the openness of the future, and the feeling that reality genuinely changes. Eternalism fits comfortably with four-dimensional spacetime and the relativity of simultaneity, while treating past events as enduring parts of reality. The growing block preserves both an existing past and an unfinished future, but must explain the physical nature of reality's advancing edge. Physics places powerful constraints on these views. Relativity makes a universal present difficult to defend. Spacetime geometry makes eternalism appear natural. Thermodynamics, causality, and quantum theory add further complications. Yet physics may not settle the argument by itself. A scientific theory can describe relationships among events, clock readings, world lines, and causal connections. Deciding whether every event represented within that theory exists in precisely the same sense may require additional philosophical assumptions. The past may have vanished, may remain within space-time, or may form the completed portion of a reality still growing towards the future. The equations narrow the possibilities. They do not necessarily choose the meaning of existence for us. Time does not merely seem to pass. It appears to have a direction. We remember yesterday, but not tomorrow. Ice melts into water, yet a pool of water does not ordinarily gather itself into a perfectly shaped ice cube. A dropped glass may shatter across the floor, but the fragments do not leap upwards and reassemble in someone's hand. Causes appear before effects. People grow older rather than younger, and the world steadily accumulates records of what has already happened. This distinction between past and future is called the arrow of time. The arrow is puzzling because many fundamental equations in physics do not strongly distinguish one temporal direction from the other. The equations describing the motion of ideal particles can often be run forwards or backwards, while remaining mathematically valid. If a recording of two perfectly elastic billiard balls colliding were played in reverse, the reversed motion could still obey the same basic mechanical laws. At the microscopic level, nature often permits processes and their reversals. The scale of rooms, weather systems, living bodies, and galaxies, however, events overwhelmingly unfold in only one familiar direction. The key to this difference is thermodynamics. During the 19th century, physicist Ludwig Boltzmann helped explain the second law of thermodynamics through statistics. The second law states that the entropy of an isolated system tends not to decrease. In ordinary conditions, systems move from lower entropy macrostates towards higher entropy macrostates. Entropy is sometimes described simply as disorder, but this can be misleading. A more precise description connects entropy to the number of microscopic arrangements compatible with a system's large-scale condition. A macrostate is the overall state visible at an ordinary scale. It may include quantities such as temperature, pressure, volume, and density. A microstate describes the exact positions and motions of the enormous number of particles producing that large-scale condition. Imagine a sealed box containing gas. If every molecule happens to be crowded into one small corner, that is a low entropy macrostate. Only a relatively small number of possible microscopic arrangements place all the molecules within that restricted region. If the gas spreads throughout the box, many more arrangements become possible. The molecules can occupy countless positions while still producing the same general appearance of evenly distributed gas. That spread-out condition therefore has higher entropy. The gas does not expand because the laws of motion forbid the molecules from returning to the corner. In principle, their movements could align in exactly the right way. The obstacle is probability. A macroscopic amount of gas contains an immense number of particles. The number of microscopic arrangements corresponding to the spread-out state is overwhelmingly larger than the number corresponding to the concentrated state. Random motion almost inevitably carries the gas towards the more probable macrostate. This statistical reasoning explains many familiar irreversible processes. Place an ice cube in a warm room, and energy flows from the surroundings into the ice. Its ordered crystalline structure breaks down as the water molecules gain freedom of movement. The ice melts, the room cools by a tiny amount, and the combined entropy of the system rises. Nothing in the microscopic laws absolutely prohibits the reverse event. Molecules in a puddle might, in principle, transfer energy into the surrounding air while arranging themselves into a neat cube, but the required coordination would be so fantastically improbable that nobody has ever needed to guard a glass of water in case it suddenly freezes itself and warms the kitchen. The same applies when perfume is released into a room. Its molecules spread through the air, moving from a concentrated region near the bottle into a much larger volume. They could theoretically gather themselves back together, but the number of dispersed arrangements is enormously greater. Milk mixes into coffee for the same reason. Once the two liquids have blended, reversing the motions of every molecule could restore the original separation. In practice, uncontrolled molecular motion carries the system towards the vastly more probable mixed state. A shattered object offers another example. When a glass falls, its organized structure becomes fragments, sound, heat, vibrations, and microscopic deformations in the floor. Reversing the event would require not only the visible pieces, but also every scattered sound wave and tiny transfer of thermal energy to converge with astonishing precision. The reverse process is not merely unlikely in the casual sense. For a macroscopic system, it is so improbable that it can be treated as physically absent on any reasonable timescale. British astrophysicist Arthur Eddington popularised the phrase arrow of time during the early 20th century. He emphasized that increasing entropy gives time its observable direction. Where entropy rises, the future lies in that direction. This thermodynamic arrow reaches far beyond melting ice and cooling drinks. It is involved in chemical reactions, weather, biological metabolism, aging, computation, memory, and the formation of physical records. Yet the second law raises another question. If entropy generally increases, why was it lower in the past? The thermodynamic arrow depends on the universe having begun in an extraordinarily low entropy state. The early universe was hot, dense, and remarkably smooth on large scales. Although matter and radiation were close to thermal equilibrium locally, gravity changes the meaning of entropy. A smooth distribution of matter has low gravitational entropy because gravity naturally drives matter to clump into stars, galaxies, and black holes. As the universe expanded, gravity amplified small density variations. Matter formed increasingly complex structures. Stars ignited, galaxies developed, planets formed, and black holes appeared. These processes allowed the total entropy of the universe to rise enormously. The direction of time experienced in a kitchen is therefore connected to the condition of the early cosmos. Milk spreads through coffee because the universe began in a special low entropy state billions of years before either milk or coffee existed. Records of the past also depend on entropy increasing. When light reflects from an object, photons carry information about its position, color, shape, and motion into the surrounding environment. Some enter eyes, cameras, or detectors. Others scatter into walls, air, and distant space. A photograph forms through chemical or electronic changes. A footprint deforms soil. A fossil forms through long physical and chemical processes. Memory involves electrical activity, molecular changes, and alterations in connections among neurons. Each record is produced by an interaction that leaves one system correlated with another. These processes consume energy, release heat, and contribute to increasing entropy. This helps explain why records point towards the past. The present contains photographs, memories, fossils, radiation, and physical damage caused by earlier events. It does not contain comparable records created by future events that have not yet interacted with the present. Human memory follows the same direction. Brains form records after events affect sensory organs and neural systems. They do not normally contain memories of events that have not yet caused any physical change in the brain. Entropy, therefore, explains much of the difference between remembering and anticipating. The past appears fixed because it has produced records. The future appears open because its events have not yet left traces in the present. But this does not answer whether past events continue to exist. Entropy explains why processes unfold asymmetrically and why evidence accumulates in one temporal direction. It describes relationships among physical states. It does not establish whether an earlier event has vanished from space-time or remains part of a four-dimensional structure. A melting ice cube leaves behind water, transferred energy, and altered surroundings. Thermodynamics explains why the ice does not spontaneously restore itself. It does not decide whether the earlier frozen state still possesses some form of existence as a past region of space-time. The direction of experience and the existence of the past are therefore separate questions. Time feels as though it moves forward because memory, causality, biological change, and increasing entropy all point in the same direction. Yesterday seems absent because consciousness occupies the present and carries only physical records of earlier events. That powerful experience should not be mistaken for proof that the past has been erased. Entropy tells us why the past is remembered and the future is not. It does not tell us by itself whether the past is still there. A memory can feel like a small opening into the past. A familiar smell returns, a voice seems to reappear, and for a moment an earlier scene becomes vivid again. Yet the brain has not travelled backwards through time. Remembering is a physical process occurring in the present. When someone recalls a childhood room, the original light is no longer entering the eyes. The earlier sounds are not reaching the ears. The remembered scene is reconstructed through present activity within the nervous system. Memories are encoded through lasting changes in the brain. Experiences alter patterns of activity across networks of neurons. Connections between neurons can become stronger or weaker, changing how easily certain patterns are activated again. These changes often involve synaptic plasticity. A synapse is the junction through which one neuron influences another. Repeated or significant activity can modify the efficiency of that connection through chemical signaling, changes in receptors, altered gene expression, and the production of proteins. One important mechanism is long-term potentiation, in which repeated patterns of activity strengthen communication between particular neurons. Long-term depression can weaken connections. Together, these processes help neural networks adapt to experience. No single neuron contains an entire memory in the manner of a tiny filing cabinet. Different features are represented across distributed brain systems. Visual details may depend heavily on regions involved in visual processing. Emotional significance may involve the amygdala. Spatial relationships and contextual information often involve the hippocampus and surrounding medial temporal lobe structures. The importance of the hippocampus became especially clear through the study of Henry Molaison, who was referred to anonymously in scientific literature for many years before his full identity became publicly known. Molaison underwent brain surgery in 1953 in an attempt to treat severe epilepsy. Surgeon William Scoville removed substantial portions of the medial temporal lobes on both sides of his brain, including much of the hippocampal formation. The operation reduced his seizures, but it also produced profound memory impairment. Molaison could remember many events from earlier life and could hold information briefly in working memory. However, he struggled to form new long-term declarative memories. Declarative memory includes consciously accessible knowledge of facts and events. Molaison could speak with a researcher, yet later fail to remember having met that person. The neuropsychologist Brenda Milner studied Molaison extensively and helped establish that the hippocampus is essential for forming many new declarative memories. His case also showed that memory is not one single ability. Molaison could still acquire certain motor skills. In a mirror drawing task, for example, his performance improved with practice, even though he did not consciously remember completing the task before. This revealed a distinction between declarative memory and forms of procedural memory involved in skills and habits. The hippocampus does not appear to serve as a permanent warehouse containing every detail of a life. Instead, it helps organize and stabilize new memories by linking information represented across different parts of the brain. This gradual process is called memory consolidation. During consolidation, a fragile recent memory becomes more stable through changes in neural activity and synaptic structure. Sleep plays an important role in this process. Patterns of activity associated with recent experiences can be reactivated, helping strengthen and reorganize memory traces across wider cortical networks. Even consolidated memories are not fixed recordings. When a memory is recalled, it can enter a temporarily flexible state. During a process called reconsolidation, the memory may be altered before it is stored again. New information, present emotions, later experiences, and the context of recall can all influence what is preserved. Remembering is therefore constructive rather than purely reproductive. A person does not open an untouched file and play the original experience exactly as it occurred. The brain rebuilds a useful version of the event from surviving information. Details may be omitted, combined, shifted, or unintentionally invented. Autobiographical memory is especially reconstructive. It combines sensory fragments, factual knowledge, emotional associations, expectations, personal identity, and later understanding. A childhood holiday may be remembered partly through direct experience, partly through photographs, and partly through stories repeated by relatives. Over time, these sources can merge until it becomes difficult to separate the original memory from information learned later. Psychologist Elizabeth Loftus demonstrated how suggestion can alter recollection and even contribute to false memories. Her research showed that the wording of questions can influence what people later report about an event. This does not mean memory is useless or normally fictional. Human memory is remarkably effective at preserving important information. It simply evolved to guide behavior rather than to provide a perfectly complete recording of every moment. A flawless archive would also be inconvenient. Remembering the precise arrangement of every breakfast cereal flake might be accurate, but it would not necessarily improve anyone's life. Memory is physical in another important sense. Creating and preserving it requires energy. Neurons maintain electrical differences across their cell membranes. They release chemical transmitters, alter receptors, activate genes, produce proteins, and remodel synaptic connections. All of this depends on metabolism and energy transfer. The brain consumes a substantial share of the body's energy, despite representing only a small fraction of its mass. Memory formation is part of this active biological process. Thermodynamics therefore applies to memory as it applies to every other physical record. Forming a memory changes matter. Energy is used, heat is released, and correlations are created between the nervous system and events in the surrounding world. A memory belongs to the same broad family as a photograph, a footprint, or a fossil. Each is a present physical state shaped by something that happened earlier. A photograph stored patterns produced when light interacted with a chemical film or electronic sensor. A fossil preserves material or an impression altered through geological processes. Tree rings reflect seasonal growth and environmental conditions. Sediment layers record deposition, erosion, volcanic eruptions, and changes in climate. The cosmic microwave background is an even older record. Its radiation preserves information about conditions in the universe roughly 380,000 years after the Big Bang. Astronomers detect it now, but the pattern reflects an ancient state of matter and radiation. These records differ enormously in form, scale, and reliability. Yet they share one feature. Each is evidence present now because a past event produced a lasting physical effect. Evidence can establish with great confidence that something occurred. It does not decide whether the event itself continues to exist somewhere within spacetime. A photograph of a wave confirms that the wave once formed. The image is not the water still moving. A memory of a conversation confirms that the brain was altered by an experience. But the memory is not the conversation continuing inside the head. This distinction matters because the existence of records and the existence of past events are separate questions. A record can survive even if presentism is true and the event itself has ceased to exist. The same record can also fit eternalism, where the earlier event remains part of space-time. Memory nevertheless gives the past a distinctive psychological character. Remembered events feel settled. They are represented as things that happened. Their outcomes are known, even when the recollection is incomplete. Anticipated events feel different because their details have not yet been fixed by experience. The future is modelled through imagination, prediction, and possibility. The past is approached through records and reconstruction. Consciousness therefore encounters a strong asymmetry. It contains traces produced by earlier events, but no comparable memory is produced by future ones. This makes the past feel closed and the future open. That feeling is grounded in real physical differences involving causality, entropy, and the formation of records. Yet it does not amount to a literal view through time. Memory brings the influence of the past into the present. It does not carry the observer back to where the past occurred. The possibility that the past still exists does not automatically mean that it can be changed. These are separate claims. An event may remain part of space-time without being accessible from the present. It may be fixed within the causal history of the universe, connected to later events through consequences and records, yet still impossible to revisit or alter. Relativity describes ordinary objects as following world lines through space-time. These world lines pass from earlier events towards later events, remaining inside future-directed light cones. A person can move through space in many directions, but their path through time is constrained by causality. Causes precede effects. A signal can influence events inside its future light cone, but not events already inside its past light cone. This structure prevents an ordinary action in the present from reaching backwards and changing the conditions that produced it. The logical difficulty becomes clear through the grandfather paradox. Imagine a traveller who journeys into the past and prevents their grandfather from meeting their grandmother. If that succeeds, the traveller is never born. But if the traveller is never born, they cannot make the journey and prevent the meeting. The action removes the cause of the action itself. The example does not need to involve a grandfather. Any attempt to change the past in a way that prevents the journey creates the same contradiction. A traveller could destroy the time machine before it is used, prevent their own departure, or deliver information that removes the reason for sending it. These paradoxes show that unrestricted alteration of the past is not merely technologically difficult, it can be logically inconsistent. One possible response is the self-consistency principle associated with physicist Igor Novikov. According to the Novikov self-consistency principle, any events involving travel into the past must remain globally consistent. A traveller may participate in earlier events, but cannot change them in a way that produces a contradiction. If someone travels backwards and attempts to prevent an event that is already known to have occurred, circumstances must ensure that the attempt fails or becomes part of the event itself. The traveller might miss, be interrupted, or discover that their actions helped produce the outcome they intended to prevent. Under this view, there is only one history. Time travel would not rewrite it. The traveller's presence in the past would always have been part of that history. This avoids contradiction, but it raises questions about freedom and probability. Events may need to align in extremely specific ways to preserve consistency. A weapon might fail repeatedly, or an unlikely interruption might always occur. The mathematics may permit such histories, though the resulting situations can feel suspiciously organized. Another proposal comes from physicist David Deutsch, who discussed time travel using ideas from quantum mechanics. Deutsch considered interactions involving closed time-like curves and quantum states. In one interpretation, a traveller entering the past may not alter the history from which they came. Instead, the interaction could be associated with a different branch or alternative history. The traveller might prevent an event in that branch without erasing the original sequence that produced the journey. This resembles the branching structure often connected with the many worlds interpretation of quantum mechanics. Such ideas remain speculative and depend heavily on interpretation. No experiment has shown that alternative branches can be used for time travel, and the physical existence of usable closed time-like curves has not been established. More ordinary changes in our understanding should not be confused with changes to the past itself. A person may remember an event differently years later. Historians may discover a new document. Scientists may reinterpret old evidence. A court may overturn an earlier conclusion after reviewing better information. These developments alter present beliefs, records, and explanations. They do not physically change the event that occurred. A forgotten conversation does not become different because someone later remembers it incorrectly. A newly discovered fossil may transform scientific knowledge of an extinct species, but it does not alter the organism's life millions of years earlier. Quantum mechanics introduces subtler questions about causal order and measurement. Some interpretations use retrocausal descriptions, in which later measurement settings help define how earlier quantum events are represented. These approaches are explored partly because quantum correlations can resist simple explanations, based only on properties fixed in advance. Retrocausality must be handled carefully. It does not normally mean that someone can send a usable message into the past or rewrite a completed macroscopic event. The observed predictions of quantum mechanics still obey strict limits on controllable information transfer. Experiments involving delayed choice or quantum erasers are sometimes described as though present decisions change what a particle did earlier. A more accurate explanation is that the complete pattern of correlations depends on the measurement arrangement and how results are compared. No recorded event in the laboratory is erased from history. No observer receives a warning from the future before choosing the experiment. The dramatic language is usually more flexible than the causality. There is currently no experimental evidence that anyone can alter a completed macroscopic event, communicate reliably into the past, or create a contradiction in causal history. General relativity contains mathematical solutions with unusual causal structures, but mathematical allowance is not proof that nature provides stable, accessible time machines. Quantum gravity may eventually clarify whether such structures are physically possible or always prevented. Eternalism does not change this conclusion. If past events remain part of a block universe, they are not necessarily editable. Their existence within spacetime may make them more like fixed locations than unfinished drafts. Every city on a map may exist, but looking at the map does not allow a traveller to move the streets or replace the buildings. In the same way, the presence of an event within space-time does not imply that an observer can revise it from a later position. The past may exist while remaining causally closed to alteration. That is a less spectacular possibility than rewriting history, but it is also far more consistent with everything physics has so far observed. Quantum physics complicates the idea that reality always possesses one completely definite history. In classical physics, a system can in principle be described by precise properties at every moment. A planet has a position and velocity. A pendulum follows a continuous path. If the state of a system were known perfectly, its earlier and later behaviour could be calculated from the laws governing its motion. Quantum mechanics uses a different kind of description. A quantum system is represented by a quantum state. This state does not always assign one definite classical value to every measurable property. Instead, it provides the mathematical information needed to calculate the probabilities of possible measurement outcomes. An electron may be described by a combination of possible positions, momenta, or spin results. A photon passing through an interferometer may be represented as taking a superposition of possible paths. Before measurement, quantum theory may not describe one ordinary classical story in which the particles simply possess the observed value all along. The quantum state evolves smoothly according to the Schrödinger equation while a system remains isolated. measurement appears to introduce something different. A range of possibilities gives way to one recorded outcome. This creates the measurement problem. The problem is not that physicists cannot use quantum mechanics. Its predictions have been confirmed with extraordinary precision. The difficulty is explaining exactly what the mathematics says happens when a measurement produces one definite result. Where does the boundary lie between a quantum system containing several possible outcomes and a measuring device displaying only one? Does the quantum state physically collapse? Does measurement merely update knowledge? Do all outcomes persist in some larger description? Different interpretations answer these questions in different ways. The Copenhagen interpretation is associated particularly with Niels Bohr and Werner Heisenberg, although the phrase covers a family of related views rather than one perfectly uniform doctrine. In broad terms, the Copenhagen approach treats the quantum state as a tool for predicting measurement outcomes. Once a measurement occurs, one definite result is recorded. Claims about unmeasured properties may have no clear physical meaning beyond the probabilities supplied by quantum theory. Bohr emphasized that experimental results must be communicated in ordinary classical language. A detector clicks in one location. A pointer settles on one value. A photographic plate contains one visible mark. This produces a definite history of recorded outcomes. Yet it leaves open the question of what, if anything, can be said about the system before those outcomes became definite. A very different proposal was introduced by Hugh Everett III in 1957. Everett's many worlds interpretation removes physical collapse from the theory. The universal quantum state continues evolving according to the Schrödinger equation at all times. When a measurement occurs, the measuring device, observer, and environment become entangled with the possible results. Instead of one outcome replacing the others, the total state develops into effectively separate branches. In one branch, the detector records one result. In another branch, it records a different result. Each observer becomes correlated with a particular outcome and experiences a definite history within that branch. The other outcomes do not vanish. They persist in branches that no longer interact in ordinary macroscopic ways. This gives history a branching structure rather than a single line. Yet many worlds remains an interpretation. It reproduces the usual experimental predictions of quantum mechanics, but physicists and philosophers continue to debate probability, branching, and what should count as a separate world. The process that makes these branches behave independently is closely connected with decoherence. Dieter Say helped establish the importance of environmental interactions in the quantum measurement problem. Wojciech Zurek and other researchers later developed the theory in greater detail. A microscopic system never remains perfectly isolated for long. It interacts with air molecules, photons, measuring equipment, thermal radiation, and countless surrounding particles. These interactions spread quantum information into the environment. The alternative components of the quantum state become entangled with different environmental states. Their phases become dispersed into an enormous number of degrees of freedom, making interference between distinct macroscopic outcomes effectively impossible to observe. A detector that has recorded one result does not normally drift back into a visible superposition of contradictory readings. The information distinguishing the alternatives has spread through the surrounding environment far too extensively. Decoherence explains why the classical world appears stable, and why different macroscopic histories stop interfering with one another. It does not by itself select one unique outcome. That remaining question depends on the interpretation adopted. Another approach is called consistent histories. This framework was developed by Robert Griffiths, Roland Omnes, Murray Gell-Mann, and James Hartle. It treats a history as a sequence of quantum events or properties occurring at different times. Quantum theory can assign probabilities to sets of histories when interference between the alternatives satisfies particular consistency conditions. Within one consistent set, physicists can discuss sequences of events without requiring continuous measurement by an outside observer. However, not every possible description can be combined into one universal classical account. Different consistent sets may provide incompatible but individually valid ways of describing the same quantum system. This suggests that the microscopic past may not always possess one complete collection of properties independent of how the questions are organized. Experiments involving delayed choices make the issue appear even stranger. John Archibald Wheeler proposed delayed choice experiments in which the final measurement arrangement is selected only after a photon has entered an interferometer. The experiment can reveal either path information or interference behavior depending on the later setup. This is sometimes described as though the later choice reaches backwards and decides what the photon previously did. That language is dramatic, but it can be misleading. Quantum mechanics predicts correlations between the preparation and the completed measurement arrangement. It does not require a classical picture in which the photon secretly chose one fixed behavior that was later rewritten. No earlier recorded result changes. No information is sent backwards to warn the experimenter about the future setting. Quantum eraser experiments create a similar temptation. In these experiments, information capable of identifying a particle's path can be preserved, erased, or measured in different ways. When results are sorted according to correlated measurements, interference patterns may appear within selected subsets of the data. The complete unsorted data does not suddenly develop an interference pattern after a later choice. The effect becomes visible only through post-selection, when researchers compare correlated groups of recorded outcomes. Nothing already observed is physically erased from history. The later measurement changes which correlations can be identified within the complete data set. Quantum theory therefore makes the idea of a unique past less straightforward than it appears in classical physics. Before stable records form, several alternative histories may contribute to the quantum state. Which history can meaningfully be assigned may depend on measurement context, interpretation, and the set of questions being asked. Once macroscopic records have formed and decoherence has spread their information throughout the environment, those records become extraordinarily stable. Quantum mechanics has not demonstrated that people can revise a completed event, remove an existing memory, or send a message backwards to create a different macroscopic past. It reveals something subtler. At the deepest level, history may not always begin as one fully classical sequence waiting to be uncovered. Yet by the time an event has left records in detectors, brains, photographs, and the wider environment, the past we encounter has become remarkably definite. The universe does not merely contain history, it has a history of its own. Cosmology is the scientific study of the universe on its largest scales. It examines the origin and evolution of cosmic structure, the behavior of space over time, the formation of galaxies and stars, and the possible future of the universe as a whole. For much of history, the universe was often imagined as eternal and broadly unchanging. Stars moved across the sky, planets followed their paths, and generations came and went beneath what appeared to be a permanent cosmic background. General relativity made a dynamic universe possible. When Albert Einstein applied his equations to the cosmos, he initially preferred a static model, yet the mathematics naturally allowed space itself to expand or contract. In the early 1920s, Russian physicist Alexander Friedmann found solutions to Einstein's equations describing expanding universes. Belgian physicist and priest Georges Lemaitre independently developed similar ideas and connected cosmic expansion with astronomical observations. Lemaitre proposed that the recession of distant galaxies could result from the expansion of space. He also suggested that the universe had evolved from a much denser earlier state. Observational evidence emerged through measurements associated with Edwin Hubble and astronomer Vesto Slipher. Slipher had already found that the light from many spiral nebulae was shifted towards longer, redder wavelengths. Hubble later established that many of these objects were galaxies far beyond the Milky Way. The general patterns showed that more distant galaxies tend to recede more rapidly. This relationship became known as the Hubble law. Galaxies are not simply flying through a fixed emptiness from one central explosion point. On sufficiently large scales, the distances between widely separated galaxies increase because space itself expands. A useful comparison is the surface of an inflating balloon. Dots drawn on the surface move apart as the balloon expands, even though none occupies a unique center on that surface. The real universe has 3 spatial dimensions rather than 2, and the balloon should not be taken too literally. But the analogy captures the idea of increasing separation. Cosmic expansion allows cosmologists to speak about cosmic time. Cosmic time is the proper time measured by ideal observers moving with the average expansion of the universe. These observers are imagined as remaining at rest relative to the large-scale distribution of matter, apart from local motions within galaxies and clusters. In a universe that is homogeneous and isotropic on very large scales, cosmic time provides a natural way to label successive stages of cosmic evolution. Homogeneous means that the universe has roughly the same average properties from place to place. Isotropic means that it looks broadly similar in every direction when viewed on sufficiently large scales. Using this framework, the age of the universe is estimated to be approximately 13.8 billion years. This does not restore Newton's absolute time. Cosmic time depends on the large-scale geometry and matter distribution of our particular universe. It is a useful physical coordinate within standard cosmological models, not a universal master clock valid in every possible space-time or for every observer. A traveller moving at high speed still accumulates a different amount of proper time. A clock near a massive object still ticks differently from a clock farther away. Cosmic time organises the average history of the expanding universe without removing the local effects of relativity. One of the most important records of this history is the cosmic microwave background. In 1965, radio astronomers Arno Penzias and Robert Wilson detected a faint microwave signal arriving from every direction. They initially encountered it as persistent background noise in a sensitive antenna at Bell Telephone Laboratories. The signal was soon recognized as relic radiation from the early universe. It had been predicted by researchers including Ralph Alpher, Robert Herman, and George Gamow. During the universe's first hundreds of thousands of years, matter existed as a hot plasma containing charged particles and radiation. Photons scattered repeatedly from free electrons, preventing light from travelling freely over long distances. As expansion continued, the universe cooled. Roughly 380,000 years after the Big Bang, electrons combined with atomic nuclei to form mostly neutral hydrogen and helium. This process is called recombination. Once free electrons became much less common, photons could travel through space with far fewer collisions. Those ancient photons have continued moving ever since, while cosmic expansion has stretched their wavelengths into the microwave region of the electromagnetic spectrum. The cosmic microwave background is therefore a physical record of the universe at an extremely early stage. Its temperature today is about 2.7 degrees above absolute zero. Tiny temperature differences across the sky reveal small variations in the early distribution of matter and energy. These variations later grew through gravity into galaxies, clusters, and the large-scale cosmic web. Several space missions have measured this radiation with increasing precision. The National Aeronautics and Space Administration launched the Cosmic Background Explorer in 1989. It confirmed that the cosmic microwave background has an almost perfect thermal spectrum and detected small variations across the sky. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped those variations in much greater detail. The European Space Agency's Planck mission later produced even more precise measurements, helping constrain the universe's age, composition, geometry, and early conditions. These observations allow scientists to reconstruct earlier cosmic states from evidence reaching the present. This reconstruction is not direct travel into the past. Astronomers do not leave the present and enter the early universe. They receive ancient radiation, measure elemental abundances, observe distant galaxies, and compare those records with physical models. The farther a telescope looks across space, the farther it also looks into cosmic history. Yet every observation still occurs now, through signals that have survived their journey. The early universe also presents a deep thermodynamic puzzle. Although it was hot and dense, it appears to have possessed extremely low gravitational entropy. Matter was distributed with remarkable smoothness, while gravity normally encourages matter to clump into dense structures. Roger Penrose has emphasized how unusual this smooth initial gravitational state was. Stars, galaxies, and especially black holes represent much higher gravitational entropy than the nearly uniform early cosmos. The low entropy of the early universe supplied the conditions required for the later arrow of time. Cosmic expansion and gravitational clumping allowed entropy to increase, making possible stars, planets, chemistry, life, memory, and records. General relativity can describe this entire cosmic development as one four-dimensional space-time. The early plasma, the formation of atoms, the first stars, the growth of galaxies, Earth's history, and the present universe occupy different regions within one geometric history. Near the apparent beginning, however, the classical description becomes incomplete. General relativity predicts conditions of extreme density and curvature, where quantum effects should become essential. A successful theory of quantum gravity may eventually reveal whether time had a true beginning, emerged from a deeper structure, or loses its familiar meaning near the earliest describable state. For now, cosmology shows that the universe has changed profoundly. The present sky contained evidence of earlier conditions stretching back almost to the beginning of observable cosmic history. Whether those earlier stages still exist as regions of space-time remains partly interpretive, but their influence is everywhere, written into the expansion of space, the structure of galaxies, and the ancient radiation still arriving from the darkness. A black hole creates one of the clearest distinctions between an event existing and an event remaining accessible. The defining boundary of a black hole is called the event horizon. It is not a solid surface and it is not a shell of matter. It is a causal boundary in space-time. Once an object crosses the event horizon, every future directed path available to it leads farther inward. Light can still move locally at the speed of light, but no future directed light signal can travel back across the horizon and reach a distant observer. This does not happen because light becomes too weak to climb out in the ordinary sense. The geometry of space-time itself has changed. Inside the horizon, escaping to the exterior is no longer one of the possible future directions. The first exact black hole solution to Albert Einstein's field equations was found by Karl Schwarzschild in 1916 only months after general relativity was completed. Schwarzschild's solution describes the space-time outside an idealized object that is perfectly spherical, electrically neutral, and not rotating. It revealed a characteristic radius now called the Schwarzschild radius. If enough mass is compressed within that radius, an event horizon forms. For an object with the mass of the Sun, the Schwarzschild radius is roughly 3 kilometers. For Earth, it would be only around 9 millimeters. Real astrophysical black holes are not expected to be perfect Schwarzschild black holes, because stars and collapsing matter usually rotate. Even so, the Schwarzschild solution remains essential for understanding the basic geometry of horizons. From the perspective of a distant observer, time appears to behave strangely near the event horizon. Imagine a probe falling towards a black hole while sending regular pulses of light back to a distant spacecraft. As the probe moves closer to the horizon, each pulse takes longer to arrive than the one before it. The light also becomes increasingly redshifted. Its wavelength stretches, its frequency falls, and each signal carries less energy when measured by the distant observer. Eventually, the pulses become so delayed, redshifted, and faint that the probe fades from practical detectability. In the coordinates used by a distant stationary observer, the probe appears to approach the horizon without ever quite crossing it. This can create the impression that the falling object becomes frozen at the boundary. Yet the physical experience of the falling observer is different. A freely falling observer crosses the event horizon in finite proper time. If the black hole is sufficiently large, nothing locally dramatic needs to happen at the crossing. There may be no visible wall, sudden flash, or conveniently placed sign announcing that returning home has become impossible. The apparent freezing is associated with the way distant coordinates describe the horizon and with the increasing difficulty of receiving outgoing signals. It does not mean the falling observer remains suspended there forever according to their own clock. This distinction reveals two valid descriptions of the same space-time. The distant observer receives signals from progressively earlier stages of the fall, increasingly delayed and redshifted. The falling observer continues along a world line and crosses the horizon after a finite duration. Once the crossing occurs, however, no later signal from the observer can reach the exterior. Events inside the black hole may still take place, but they become causally hidden from the outside universe. Rotating black holes possess an even richer structure. In 1963, New Zealand mathematician Roy Kerr discovered an exact solution describing a rotating black hole. The Kerr solution is considered a much more realistic model for astrophysical black holes because collapsing stars almost always carry angular momentum. A rotating black hole drags nearby space-time around with it. This effect is called frame dragging. Outside the event horizon lies a region called the ergosphere, where space-time is dragged so strongly that no observer can remain stationary relative to distant stars. Objects within the ergosphere may still escape, but they are forced to rotate in the same general direction as the black hole. The causal structure of an idealized Kerr black hole differs from the simpler Schwarzschild case. The mathematical extension contains an outer horizon, an inner horizon, and a ring-shaped singularity rather than a point-like one. Some idealized regions of the full mathematical solution contain highly unusual possibilities. However, the inner structure is expected to be unstable, and realistic black holes formed through collapse may not preserve every feature of the perfectly extended Kerr geometry. The central lesson remains clear. A horizon separates events that can communicate with the outside universe from events that cannot. Those hidden events may remain part of space-time. Their world lines do not necessarily disappear at the moment they become unobservable, yet exterior observers can no longer receive new information from them. This creates a sharp distinction between existence and observability. A second distinction concerns information. During the 1970s, Jacob Bekenstein argued that black holes possess entropy, proportional to the area of their event horizons. Stephen Hawking later showed that quantum effects cause black holes to emit thermal radiation. Hawking radiation means that a black hole is not perfectly black. It can gradually lose mass and, over an extraordinarily long period, may evaporate. For a black hole with several times the mass of the Sun, the evaporation time would be vastly longer than the current age of the universe. The process is therefore negligible for ordinary astrophysical black holes today, but conceptually it creates a major puzzle. If the Hawking radiation is completely thermal and contains no information about the matter that formed or entered the black hole, then the black hole could eventually disappear while the information about its past vanished with it. This is the black hole information paradox. In quantum mechanics, unitarity is the principle that the evolution of an isolated quantum system preserves information. The present quantum state should, in principle, retain enough structure to be connected consistently with earlier states. Complete information destruction would therefore conflict with the central principle of quantum theory. Don Page studied how information might emerge during black hole evaporation. The Page curve describes the expected behavior of entanglement entropy if evaporation preserves information. At first, the radiation appears increasingly entangled with the remaining black hole. After a characteristic stage, often called the Page time, information would need to become recoverable from correlations within the outgoing radiation if the entire process is unitary. Ideas associated with Gerardus 't Hooft and Leonard Susskind helped develop the holographic principle. This principle suggests that information contained within a region of space may be represented on a lower dimensional boundary. Modern work on black holes, holography, quantum extremal surfaces, and related models has strengthened the case that information may ultimately be preserved. Even so, exactly how this preservation works for realistic black holes remains part of ongoing research in quantum gravity. The issue is directly connected to the reality of the past. Matter falling into a black hole carries records of earlier events. Its structure, quantum state, temperature, composition, and motion all reflect its history. If that information is preserved, then some description of the past remains encoded, even when ordinary observation becomes impossible. If information is truly destroyed, then black holes would do more than hide the past. They would erase part of its physical recoverability from the universe. These possibilities must be kept separate. An event may exist within spacetime while remaining unobservable. Information about it may survive while being impossibly scrambled, or it may be permanently lost depending on the final theory of black hole evaporation. Black holes therefore turn one question into three. Did the event happen? Does it still belong to space-time? Can any information about it ever be recovered? Those questions sound similar, but a horizon shows that they are not the same. General relativity usually preserves a clear local direction of time. A traveller moves from earlier experiences towards later ones, carrying a clock that steadily accumulates proper time. Yet some mathematical solutions to Einstein's equations contain paths that curve through space-time and eventually return to an earlier event. These paths are called closed timelike curves. A timelike curve is a possible route through space-time for an object moving more slowly than light. Along such a path, the traveller always experiences time moving forwards locally. Their heartbeat continues normally. Their clock advances. They never feel themselves reversing into yesterday. A closed, time-like curve is unusual, because the path eventually loops back to an event in its own past. The traveller moves forwards at every local stage, yet the full geometry returns them to an earlier part of space-time. This is not the same as simply moving very quickly and experiencing time dilation. Relativistic travel can carry someone far into the future of observers who remained behind, but ordinary time dilation does not return them to an earlier event. A closed Timelike curve would allow a genuinely circular causal history. The existence of these solutions shows that general relativity does not automatically forbid every mathematical form of travel into the past. One famous example was discovered by Kurt Gödel in 1949. Gödel found a solution to Einstein's equations describing a universe filled with matter and rotating as a whole. In Gödel's universe, the global rotation tilts light cones in such a way that sufficiently long journeys could follow closed time-like curves. A traveller might move through space while always advancing according to their own clock, and eventually return to an event before their departure. The result was important because it showed that Einstein's equations alone do not guarantee a universal division between past and future across every possible space-time. However, Gödel's model is not considered an accurate description of the observed universe. Modern cosmological measurements do not show the required global rotation. The model also differs from our universe in its expansion history and large-scale structure. It remains a mathematically valid space-time, but physical validity requires more than mathematical consistency. Another proposal involves an object called a Tipler cylinder. Physicist Frank Tipler explored an earlier idea associated with Willem Jacob van Stockham. The model considers an extremely dense, rapidly rotating cylinder. Its rotation would drag space-time around strongly enough that certain paths near it could become closed time-like curves. The idealized version requires a cylinder of infinite length. A finite cylinder would need conditions so extreme that constructing one appears physically implausible. It would have to be extraordinarily dense, rotate at an enormous speed, and avoid collapsing or tearing itself apart. An infinite rotating cylinder is particularly inconvenient because infinity is not generally available from an engineering supplier. The Tipler cylinder therefore demonstrates another possibility within idealized general relativity, but it does not provide a practical design for a time machine. Traversable wormholes offer a more familiar route in theoretical discussions. A wormhole is a hypothetical connection between separated regions of space-time. The simplest Einstein-Rosen bridge, associated with Albert Einstein and Nathan Rosen, is not traversable. It closes too quickly for matter or light to pass through from one exterior region to another. In the late 1980s, Michael Morris and Kip Thorne studied whether a wormhole could remain open long enough to be crossed. Ulvi Yurtsever later joined work exploring the implications for time travel. A traversable wormhole would have two entrances, often called mouths, connected by a shorter interior route. If one mouth experienced significant time dilation through rapid motion, or strong gravity, and was then returned near the other, the two mouths could become temporally offset. A traveller entering one mouth might emerge from the other at an earlier external time. If the arrangement allowed the traveller to return to the starting location before departure, a closed time-like curve could form. The difficulty lies in keeping the wormhole open. Traversable wormhole models generally require exotic matter with negative energy density relative to certain observers. Ordinary matter does not possess the necessary large-scale properties. Quantum field theory can produce limited negative energy effects under special conditions, such as those related to the Casimir effect. However, quantum inequalities appear to restrict how much negative energy can exist, how long it can persist, and how widely it can be distributed. There is no evidence that the enormous, stable negative energy configuration needed for a human-sized wormhole can exist. Even if a suitable wormhole formed, quantum effects might destabilize it as soon as it approached becoming a time machine. Stephen Hawking proposed the chronology protection conjecture in 1992. The basic idea is that the laws of physics may prevent closed time-like curves from forming on macroscopic scales. As a spacetime approaches the creation of a chronology horizon, where closed time-like curves first become possible, quantum fields may develop extremely large energy densities. Their gravitational effects could disrupt the geometry and destroy the time machine before it operates. The conjecture remains unproven because a complete theory of quantum gravity does not yet exist. Still, it expresses a widely considered possibility that quantum physics protects ordinary causal order. No observation has revealed a traversable wormhole. No closed time-like curve has been detected. No experiment has demonstrated a method for returning information, matter, or a traveller to an earlier macroscopic event. Black holes, gravitational waves, frame dragging, and relativistic time dilation are real and well tested. Time machines are not. A closed time-like curve would also create difficult questions about causality. An event could help cause itself. An object might exist in a loop without ever being created in the ordinary sense. A traveller could receive information from an older version of themselves and later become the person who sends it back. This is sometimes called a bootstrap paradox. A design, message, or object circulates around the loop, but there is no clear point at which it originated. Such a space-time would blur the distinction between occurrence and continued existence. An event would not simply happen once and recede into an inaccessible past. It would belong to a circular causal structure that could be encountered again along the same world line. That possibility is mathematically fascinating, but fascination is not evidence. Einstein's equations admit many idealized solutions containing conditions that the actual universe may never realize. Some require infinite structures, unrealistic matter distributions, unstable horizons, or energy conditions unlike anything available on useful scales. A solution can reveal what a theory permits under stated assumptions. It does not prove that nature supplies those assumptions. Space-time may be flexible enough on paper to loop backwards. Whether the real universe ever allows such a loop remains entirely unconfirmed. General relativity and quantum mechanics describe time in very different ways. In general relativity, space-time is dynamic geometry. It is not a fixed stage on which matter performs. Energy and momentum shape space-time, while the geometry of space-time influences the motion of matter and light. Time is woven into this geometry. Clocks follow world lines through curved space-time, and the amount of proper time they measure depends on the path they take. Quantum mechanics usually begins from a different picture. A quantum state changes with respect to an external time parameter. The Schrödinger equation describes how that state evolves from one moment to another. In ordinary laboratory physics, this causes little difficulty. A clock outside the system can mark the duration of an experiment. Researchers prepare a particle, allow it to evolve, and measure it later. The difficulty appears when physicists try to describe the entire universe quantum mechanically. If the universe includes every clock, every observer, and every physical system, there is no obvious external clock left outside it. Nothing beyond the universe is available to announce that one universal moment has become the next. This conflict is known as the problem of time in quantum gravity. A theory of quantum gravity must somehow combine general relativity, where time is part of a changeable geometry, with quantum mechanics, where time normally acts as an external parameter. One important attempt led to the Wheeler-DeWitt equation, associated with John Archibald Wheeler and Bryce DeWitt. The equation applies quantum principles to the geometry and matter content of the universe. In its basic form, it does not contain ordinary time evolution of the familiar Schrödinger kind. Put simply, the equation appears to describe a universe that is globally stationary. This does not mean that nothing happens in everyday life. Clocks still tick, planets move, and people continue to misplace objects with reassuring consistency. The puzzle is how this apparent change emerges from a fundamental description in which no external time variable appears. Some physicists and philosophers have taken this possibility seriously and ask whether time may not be fundamental at all. Julian Barber has argued for a timeless view based on configuration space. In this picture, the basic elements of reality are complete possible arrangements of the universe, rather than objects evolving through an independent time. Each arrangement represents a total configuration of matter and geometry. Barber sometimes describes richly structured configurations as time capsules, because they contain records that appear to refer to other configurations. A configuration might include fossils, memories, photographs, worn objects, and patterns in radiation. These features create the appearance of a past even if reality at the deepest level consists only of complete timeless arrangements. Motion would then be understood through relationships among configurations rather than through objects travelling along a fundamental temporal stream. This proposal is radical. It suggests that history may arise because some configurations contain information that makes them look as though they developed from others. Carlo Rovelli offers a different but related relational approach. In relational physics, time is not necessarily one universal quantity flowing independently of the systems being described. Instead, temporal statements emerge from correlations between physical variables. One system can act as a clock for another. A pendulum changes while a planet moves. An atomic transition marks a duration while a photon travels. A heartbeat can be compared with the changing position of the sun. Time is therefore expressed through relationships among changes. This view fits naturally with general relativity, where there is no single universal clock. Different systems follow different world lines and measure different proper times. At the fundamental level, the meaningful question may not be what a system does at an external time, but how one physical quantity changes relative to another. A further proposal was developed by Don Page and William Wouters. The Page and Wouters mechanism explores how apparent time evolution can emerge from quantum correlations within a globally stationary state. Imagine dividing the universe into two parts. One part acts as a clock, while the other is treated as the system being observed. The combined quantum state may remain unchanged globally. Within that stationary total state, however, the condition of the system can be correlated with different readings of the clock. An observer inside the universe would then describe the system as evolving relative to the clock. From the outside, if such an outside viewpoint were meaningful, the total state would not change. From within, one subsystem would appear to pass through a sequence of states as another subsystem records successive values. Timelike behaviour would emerge from entanglement and correlation. Alanconi and Carlo Rovelli proposed another idea called the thermal time hypothesis. This approach connects the flow of time with the statistical state of a physical system. Instead of assuming time first and describing how the state changes within it, the state itself may determine a natural temporal flow. Thermodynamics already gives time an observable direction through increasing entropy. The thermal time hypothesis goes further by suggesting that a suitable notion of time may emerge from the statistical structure of the system being studied. Different states might therefore define different effective flows of time. These proposals do not all describe the same mechanism. Some remove time almost entirely, others treat it as relational, statistical, or emergent from quantum correlations. They remain active areas of theoretical research. No timeless or emergent time model has yet replaced ordinary time across all tested physics. General relativity and quantum field theory continue to describe observations with remarkable success in the domains where they apply. A complete and experimentally confirmed theory of quantum gravity has not yet been established. It is therefore too early to say that time has definitively been shown to emerge from something deeper. Still, the possibility changes the question of whether the past exists. If time is fundamental, past events might be treated as regions within spacetime or as moments that have ceased to exist. If time is emergent, the past may be better understood as a pattern of correlations, records, and relationships within a deeper, timeless structure. A memory would not point towards a separate place called the past. It would be part of a present configuration whose internal structure encodes apparent history. The distinction between before and after might arise from entropy, information, quantum entanglement, or the ordering of physical changes. In that case, asking whether the past still exists may assume more than nature provides. There may be no fundamental past waiting somewhere behind the present, but there may also be no fundamental present moving forwards through time. There may instead be a network of physical relations from which the experience of history gradually emerges. So, does the past still exist? Physics can take this question surprisingly far, but it cannot answer every part of it without help from philosophy. The most useful approach is to separate what experiments have established from the interpretations built around those results. The strongest established conclusion comes from relativity. Modern physics does not provide one universal present shared by every observer. Two observers moving relative to one another can disagree about which distant events are happening now. Their disagreement is not caused by faulty clocks or delayed vision. It follows from the structure of space-time. Special relativity therefore removes the simple Newtonian picture in which the whole universe passes through one common moment. Hermann Minkowski's formulation of space-time offers a natural replacement. Events are represented as points within a four-dimensional geometry. Objects trace world lines through that geometry. Like cones, determine which events can influence one another, and proper time measures the duration experienced along each path. General relativity extends this picture by allowing space-time itself to curve. Planets, clocks, people, light rays, stars, and black holes all follow trajectories through the same dynamic geometry. Within this framework, an event does not need to vanish from the mathematical structure when it ceases to be present for an observer. A childhood afternoon, a supernova explosion, and the formation of Earth can all be represented as different regions of space-time. This is why relativity strongly supports the block universe interpretation, also called Eternalism. According to this view, past, present and future events all belong to reality. They occupy different temporal locations, just as cities occupy different spatial locations. An observer experiences only a limited portion of a world line, but the remaining events do not have to be declared non-existent. However, this conclusion should not be overstated. Relativity has been tested extensively. Time dilation, gravitational redshift, the relativity of simultaneity, and the behavior of light all belong to successful physical theory. The claim that every event exists equally is an interpretation of that structure. It is not a separate experimental result displayed directly by a detector. A philosopher may accept relativity while arguing for presentism, perhaps by adding a preferred but hidden notion of simultaneity. Another may defend the growing block universe. Such views face serious difficulties, but relativity alone does not force everyone to use the word existence in exactly the same way. Thermodynamics also clarifies part of the mystery. Entropy explains why time has an observable direction. It helps account for aging, memory, spreading heat, chemical change, broken objects and the formation of records. The past leaves traces because earlier events have interacted with the present. Photons scatter, brains change, photographs form, rocks are marked, genetic information is inherited, energy is transferred, and entropy generally increases. The future does not leave the same kind of records because future events have not yet interacted with the present. Yet entropy does not prove that earlier events have been erased from reality. It explains why processes are irreversible in practice, and why memory points in one direction. It does not decide the ontology of the past. Quantum mechanics makes the situation more subtle. At microscopic scales, a quantum state may contain several possible outcomes rather than one fully definite classical history. Measurement raises the question of when possibilities become recorded facts. Different interpretations answer differently. The Copenhagen interpretation emphasizes definite outcomes. The many worlds interpretation allows different outcomes to persist in separate branches. Consistent histories permits probabilities to be assigned to compatible sequences of quantum events. Decoherence explains why alternative macroscopic outcomes stop producing observable interference. Interactions with the environment spread quantum information so widely that stable records emerge. Once an event has affected detectors, air molecules, photons, computers, and brains, its macroscopic history becomes extraordinarily difficult to reverse. Quantum physics therefore complicates the idea of one simple microscopic past. It does not show that a completed everyday event can be freely rewritten. No accepted experiment has allowed anyone to revisit their own completed past. No reliable signal has been sent backwards to change an earlier decision. No macroscopic event has been removed from history after it occurred. General relativity contains mathematical spacetimes with closed time-like curves. Wormholes and other speculative structures may allow unusual causal paths under extreme assumptions, but no observation shows that such routes exist in usable form. It is therefore helpful to separate four different claims. The first is that the past happened. Evidence for this is overwhelming. The second is that evidence of the past remains. Memories, fossils, radiation, records, and the present arrangement of matter all demonstrate this. The third is that past events continue to belong to space-time. Relativity makes this a natural and powerful interpretation, though the meaning of existence remains partly philosophical. The fourth is that the past is presently accessible. Physics provides no evidence that it is. These claims are related, but they are not interchangeable. An event may have happened and left evidence without remaining accessible. It may belong to space-time without still occurring. Information about it may survive even when direct observation is impossible. The most defensible answer is therefore conditional. Under the space-time interpretation most naturally associated with relativity, the past remains part of reality. Earlier events occupy their own regions within the four-dimensional structure of the universe. They are not still happening in the present. They cannot ordinarily be revisited. They do not remain available for alteration. The past may still exist, but not here and not now. That leaves one final difficulty. If fundamental physics can describe a universe without one objectively advancing present, why does consciousness experience time as moving? Why does one moment feel immediate, the previous one remembered, and the next one unknown? Physics can describe clocks, world lines, entropy, causality, and memory formation. Neuroscience can study how brains construct temporal experience. Philosophy can analyze what existence and becoming mean. Yet the felt passage of time remains unresolved. Perhaps the moving present is fundamental. Perhaps it emerges from memory, prediction, and entropy. Or perhaps consciousness experiences only one narrow region of a much larger temporal reality. The equations reveal that the universe does not possess the simple shared now that everyday intuition suggests. What they do not yet explain is why living inside that universe feels so much like time is carrying us forward. Does the past still exist? The most careful answer is that the past may no longer be happening, but modern physics does not clearly describe it as having been erased from reality. For centuries, the simplest picture was the one formalized by Isaac Newton. Time flowed uniformly throughout the universe, and every object shared one universal present. One complete state of reality existed, then gave way to another. Within that framework, the past could be imagined as something that had simply disappeared. Albert Einstein's theories of relativity changed that picture. Motion affects elapsed time. Gravity affects elapsed time. Most importantly, observers moving relative to one another do not always agree about which distant events are happening now. There is no single universal presence stretching across the cosmos. Hermann Minkowski united space and time into four-dimensional spacetime, where events occupy locations and objects trace world lines between them. Light cones divide events according to causal connection, separating what can influence an observer from what remains inaccessible. Gravitational time dilation shows that different clocks can follow different paths and accumulate genuinely different durations. The universe does not appear to advance according to one cosmic master clock. Entropy explains why time has a direction. Heat spreads, objects break, living bodies age, and physical records accumulate. Memory preserves traces of earlier events through present changes in the brain, while fossils, tree rings, sediment, radiation, genetic inheritance, and the arrangement of matter carry evidence of previous conditions. Yet a record of the past is not the past event itself. A photograph is not the light still falling on the original scene. A memory is not a literal return to an earlier moment. Ancient radiation arriving at a telescope is evidence of what happened, not direct access to the place and time where it began. Quantum physics makes history less straightforward at microscopic scales. Possible outcomes can coexist within a quantum state, while measurement, environmental interaction, and decoherence produce stable macroscopic records. Cosmology reconstructs the universe's development from the cosmic microwave background, galactic structure, and expansion. Black holes raise the further question of whether information about events can become permanently hidden or fundamentally lost. None of this proves that the past is still available. Eternalism, or the block universe interpretation, treats past, present, and future events as permanent regions of space-time. Presentism maintains that only the current moment exists. The growing block universe preserves an existing past while allowing reality to expand into an unfinished future. Each view protects something important. Eternalism fits naturally with relativity. Presentism preserves the special reality of now. The growing block preserves both a real past and genuine becoming. Yet presentism and the growing block must explain why one present should be physically privileged, when relativity provides no universal simultaneity. Even if the past remains part of space-time, it would not follow that it is active, changeable, or reachable. An earlier event could exist at its own temporal location without continuing to occur. It could remain part of reality without allowing anyone in the present to experience it again. Existence is not the same as accessibility. A distant city may exist even when it cannot be reached from where someone stands. The past may be similar, although the barrier is causal rather than merely geographical. A future theory of quantum gravity may alter this picture completely. Time may prove to be emergent from deeper relationships involving change, information, quantum correlations, or thermodynamics. In that case, asking where the past exists may be less useful than asking how physical systems preserve the structure we interpret as history. For now, physics suggests that reality may extend more deeply through time than human experience reveals. The past may not have vanished. It may simply no longer be where we are. And why consciousness experiences one moment arriving, another fading, and the next waiting beyond reach remains one of the quietest and deepest mysteries in nature,